Okay, this is Mr. Asher, and this is for Chem 121. And I'm going to do this short video trying to explain how you look for uh, reduction oxidation processes or oxidation reduction processes in a chemical reaction. And hopefully this will be a little clearer than the presentation I gave in class. And I'm going to turn off my video so there's not a little section of the whiteboard that I can't see that's covered by my face. So hopefully that is gone out of the picture. So let's take a really simple reduction oxidation process, and that's the formation of water. And that balanced chemical equation is two hydrogen molecules plus one oxygen molecule. Off to a great start here. One oxygen molecule, and that forms two water molecules, H2O. And you can see this is balanced. I got two oxygen atoms here, two over here, four hydrogen atoms, and four hydrogen atoms. But let's take a look at what's going on here. If we look at the Lewis diagram for a hydrogen molecule, we've got hydrogen with one electron and another hydrogen with one electron, right? And if we look at the Lewis diagram for an oxygen molecule, we've got one oxygen with 6 electrons and a second oxygen with 6 electrons. So that there's a double bond between the oxygen, and each oxygen has 8 electrons, right? In their octet, right? So those are the electron dot structures. And if we calculate the formal charge on each atom in these molecules, remember you divide the electrons so that half go with one atom and half go with the other atom, so that in this molecule, each hydrogen atom has 1 electron. So the charge here on the hydrogen is 0 because each has 1 electron. Okay. And in the oxygen atom, half the electrons go with that oxygen and half go with the other oxygen. So the charge on each oxygen atom is 0. Okay. So each atom here is starting out as a charge of 0. Okay. And over here, by definition, if you remember the definition, by definition, oxygen, whenever it's bounded with something else, has a charge of 2 minus. And that means to make this compound charge balanced, right? If oxygen is 2 minus, because by definition, oxygen is 2 minus in that compound, then each hydrogen has to be plus. Why? Because if it's not, then the molecule isn't charge balanced. So each hydrogen has to be plus 1, oxygen is 2 minus, and that gives us this overall charge balance. Well, now if you look at what had to happen to these atoms, hydrogen at 0 to get to hydrogen plus had to lose an electron. Why did that happen? Because here we've got hydrogen with 1 proton and 1 electron for a total charge of 0. And over here, this hydrogen still has 1 proton, but to get the charge of 1 plus 1, it has to have 0 electrons. Well, you have to conserve electrons, right? So that means that some of this electron came off, right? And if you look at oxygen, oxygen went from 0, meaning it had 8 protons and 8 electrons, to oxygen 2 minus, right? Well, oxygen 2 minus still has 8 protons, but to be a 2 minus, it has to have 10 electrons, because 8 minus 10 is equal to minus 2, right? So that means over here, oxygen had to gain 2 electrons to get to oxygen 2 minus. So you see what happened is the hydrogen atom lost electrons, and we call that oxidized, because being oxidized, oxidation is losing electrons. And the oxygen gained electrons, we call that reduced, because reduction is the gain of electrons. So if you look at overall what happened in this reaction, we have 2H2, right? 2H2, which is the same thing as 4 hydrogen atoms. And each one went to H plus an electron. Right? So that those 4 hydrogen atoms released a total of 4 electrons. And the oxygen atoms, there are 2 oxygen atoms, and each one of those took up 2 electrons to become oxygen 2 minus. And so in total, these took up 4 electrons. And you notice the number of electrons released by the hydrogen matches the number of electrons taken up by the oxygen. So hydrogen was oxidized and produced 4 electrons. Oxygen was reduced, and 2 oxygen atoms each took up 2 electrons for 4 total electrons. And overall now, you've got H2O, which is charge balanced, but it's a reduction oxidation process, okay? So in a reduction oxidation reaction, you have to produce the same number of electrons through oxidation that are taken up by reduction. And that will be true for every oxidation reduction reaction, okay? So let's look at a little more complicated example, right? That came also from, well, it isn't in the worksheet, but let's look at the reaction of 2 sodium metal plus water. And this goes to, I'm sorry, I've got it balanced wrong. I'll have to go back and do this. And this goes to NaOH. No, I've got this right. 2 NaOH plus H2. H2, H2O. Hang on, don't panic, anybody. I think I need 2H2O. Right, that's right. Okay. Okay, so this is balanced because I've got 2 sodiums here, 2 sodiums here. I have 2 times 1 oxygen here, 2 oxygens here. And I've got 2 times 1 for 2 hydrogens, plus 2 more is 4, and then I've got 2 times 2, so 4 hydrogens, okay? Now, you know this is a redox process because sodium is starting out here as Na0, and it ends up over here in this ionic compound, NaOH. And remember the hydroxyl ion, OH, has a charge of -1, which means that sodium ends up as Na+. And just like before, sodium starts out as 0 with 11 protons and 11 electrons, but it ends up as Na+, which will still have 11 protons, now it only has 10 electrons. So that sodium 0 went to sodium plus 1 electron, right? Because it ends with a net positive charge. And over here on this side, remember, just like before, oxygen is 2 minus and H is plus 1, is 1 plus, right? So H plus went to plus 1 electron, went to H naught, H0, because this is molecular hydrogen. And just like before in the reaction of water, hydrogen in its molecular form starts out at charge 0. So hydrogen here went to 0. So it starts out as plus 1. So hydrogen was plus 1 here, and it starts out as, and it ends up as 0, which means that hydrogen had to gain an electron. So you can see the charge, the oxidation reduction coupling here, where sodium got oxidized and hydrogen was reduced. In other words, sodium got rid of an electron and gave it to one of the hydrogens here, and then it did that twice to make one hydrogen gas molecule. Right? So sodium oxidized, hydrogen is reduced, and you're left with an ion in the form of sodium ion, and then elemental hydrogen. So hydrogen got reduced by that process. Now I'm going to do one more example, and this is a combustion. So we've got 2C6H6 plus 15O2, and this is going to 12CO2 plus 6H2O. You know what? This is too complicated. I'm not going to do this one because it's just going to confuse everybody. Let's do a simpler combustion reaction. Let's do this one. We have CH4 plus 2O2, and that goes to CO2 plus 2H2O. Okay, now remember our rules, right? One is that hydrogen is always plus 1. So that means hydrogen here, H, is 1 plus. We'll just write that as H plus, right? Because hydrogen is always H plus. And there's 4 of them. So it's 4 times H plus, 1, which is a total charge of 4 plus. And if hydrogens give 4 plus total, that means carbon has to be 4 minus, or else methane, CH4, is in charge balance. So carbon starts out as 4 minus. And now if we look over here on the right, remember oxygen is always 2 minus, and there's 2 oxygens. So that means the total negative charge here is 4 minus, which means that carbon has to be 4 plus. Otherwise, carbon dioxide isn't balanced, which means that this carbon 4 minus went to carbon 4 plus, and it liberated 8 electrons because it went from -4, -3, -2, -1, 0, 1, 2, 3, 4. So it went down 1, 2, 3, 4, 5, 6, 7, 8. 8 steps. Lost 8 electrons and became more and more positive. Okay. So carbon did that, right? And now oxygen, you know, it starts off again as 0 because it's molecular oxygen. And it ends up as 2 minus there and as 2 minus there. So oxygen plus 2 electrons went to oxygen 2 minus. And there are 2 times 2, so 4 total oxygen atoms did this. And the total here is 8 electrons. And you notice that hydrogen was just along for the ride. It starts off as plus 1 here, and it ends as plus 1 here. And so carbon is oxidized, and oxygen is reduced. Therefore, this combustion process is an oxidation reduction reaction. Okay. Now, let's look at a little more complicated example, and one that's from the homework, and we'll hope I get it balanced correctly this time. So let's look at, and this is one we didn't do in class, and I don't think we did 5, 6, 7, or 8 in class, but I'll do those separately. But I'm just going to do this one here as an example, where if we have copper solid plus nitric acid, and that goes to copper nitrate plus NO2 plus H2 gas, right? And so now we have to balance this. And one copper, I think we need 4 of these. And then we get 1 of those, 2 of those, and 2 H2s. I believe that's balanced. So let's make sure it's balanced. So we have 4 times 3 oxygens, so 12 oxygens. 2 times 3 is 6. Plus 2 times 2 is 4, so that's only 10 oxygens. But we've got the right number of nitrogens. So okay, there's no way to get this to work. This must be 2H2O. There, that's what it is. It's 2H2O. That's the reaction. And this will balance. That the copper, there's 1 copper, 4 hydrogens. 2 times 2 is 4 hydrogens here. There are 4 nitrogens. There are 2 times 1, so 2 nitrogens, 4 nitrogens, and there are 12 oxygens over here, 4 times 3, and there's 2 times 3, which is 6, plus 2 times 4, which is 10, and then 2 more is 12. So this is the balanced reaction. And now let's figure out what the redox processes are. So copper over here is starting out as Cu0. It's in its elemental state, and it's going over here to Cu2+, which means it had to liberate 2 electrons. How do I know it's 2+? Because each nitrate ion is NO3-, right? And there's 2 of them, which means the total charge here is 2-, which means copper has to be 2+. Okay. And now the 2 nitrates that do this, nothing happens to them, right? But now if we look at nitrogen, a nitrate ion, just going to do a little sidebar over here, NO3-, and we look at nitrogen, and then we figure out that in this compound, nitrogen is each oxygen, remember oxygen is always 2-, so that we have 3 oxygens, O2, 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 and each one is 2-, 2-, 2-. And then we have the nitrogen, right? And the total charge on all of these things has to be 1-, which means nitrogen has to be 5+. Why does nitrogen have to be 5+? Because the total here is 6-, and 5+ gives me the net charge on the ion of 1-. So nitrogen is starting out as 5+. Okay. And over here, this nitrogen is still 5+ because it's still nitrate. But this nitrogen is not. If we look at NO2, right? Oxygen is still 2- because it's bonded to something that isn't oxygen. So we have 2 oxygens, each at 2-, and the total negative charge on that is 4-, which means nitrogen has to be 4+ because NO2 is neutral. Okay. So nitrogen is 4 plus. So that means nitrogen got an electron and went to N4 plus. Yeah. And this is our redox pair. Copper was oxidized, nitrogen was reduced. But there's two nitrogens because we formed two NO2s. So a second nitrogen went to N4 plus as well. For a total of 2 electrons taken up, 2 electrons released. Okay. So when you look at redox processes, find something that either starts or ends at its elemental state, or look for things that changed their formal charge, right? That changed their change, using the simple rule that oxygen is always 2 minus when it's not bonded to oxygen, and that hydrogen is always 1 plus. And if you use those two rules, you can figure out most of the time what's going on and look for elements that are produced or produced or consumed. All right, I'm going to stop there and I'm going to move on to other things. Talk to you later.